Alright, section 8-4, space figures and nets. Let's actually get rolling here with our lesson objectives, which are to use nets of space figures and to analyze and identify nets of space figures. Let's actually look at our key concepts and vocabulary, and we start with the definition of what is a polyhedron. A polyhedron, oops, that's supposed to be an H. Polyhedron. A polyhedron is a three-dimensional figure whose surfaces are polygons. Each polygon is a face of the polyhedron. An edge is a segment that is formed by the intersection of two faces. Then we have a vertex. A vertex is a point where three or more edges intersect. And then we have a net. A net is a two-dimensional pattern that you can fold to form a three-dimensional figure. One of the simplest such figures happens to be a cube. And in a cube, a polyhedron, which actually a cube is a polyhedron with 6 faces, each of which it happens to be a square. Let's take a look at this polyhedron that we have here on the right, this guy right here. As you can see, the top and bottom they look to be squares. Then the sides, the other faces, are rectangles, and each of the faces happens to be a two-dimensional figure. 2 squares and 4 rectangles. The sides of the figures, of the two-dimensional figures, they actually are known as our edges. So when we're talking about edges, we're talking about where the sides of the two-dimensional figures intersect. And the vertex, or the vertices, is pretty much the corners of each of the actual figure, the outside corners of the three-dimensional figure formed. We're going to take a look at that in a little bit. So let's take a look at our first example here. And it says, identifying a net. Is the pattern a net for a cube? If so, name the letters that will appear on opposite faces. All right. Since I am not an artist, actually, I'm just going to make the image appear momentarily. So we start here with this two-dimensional figure. All right. We have 1, 2, 3, 4, 5, and 6 two-dimensional figures. They're actually joined. As you can see, each side actually meets the other side. So what figure can we actually make? A cube does have 6 faces, but let's see if this will actually work. So if we were to take this figure and fold it right along those edges that we see, we're going to start seeing the shape take actually, we're going to see the pattern take shape, rather. So we'll see how that goes. Let's take a look at what it looks now after the modification. All right, so as soon as we start folding the image or the two-dimensional figure, you start seeing how this will come together to form a three-dimensional figure, which, as I mentioned before, we can actually fold through our edges right here, and we fold along the edges to form a three-dimensional figure. If we complete the folds, our figure will end up looking like this. So we can see that as we can fold the figure or fold the two-dimensional net, we have that net right there. We start folding it along the edges, and we come up with this figure right here, and this indeed happens to be a cube. So we take a look at what are the letters that would be in opposite ends or opposite sides, opposite faces. We can see, based on the second figure right here, that opposite, well, we have B and D. B and D will end up being opposite sides, right? So we can, when we fold this side this way and we take this side and fold it this way, the B and D are going to be in opposite ends. So we have B and D. B and D are going to be in opposite ends. All right. When we actually fold the rest of it, we're going to see, well, the tops and the bottoms. We can see that F and E are going to be in opposite ends. So we have F and E are going to be in opposite ends. And we see that if we finish closing it, when A comes over here, C stays where it is, but A will come up and it will be opposite sided to what A is. So we have A and C. A and C, that's what I meant to say. A and C will be in opposite sides. Do we have 6? We have 2, 2 and 2, 3 sets, which is 6 sides, which is what we end up having, 6 faces. So that's, indeed, it actually comes out to be a cube, and those are the pairs of opposite faces. All right. Now, your example to do, and yes, you're doing this example. Fun stuff, right? All right. So it's just for you to try to sketch it. So sketch the 3-dimensional figure that corresponds to the net below. All right. Take a look at it. It has 3 rectangles in it, right? 1 rectangle, 2 rectangles, 3 rectangles, but it has triangles on the first rectangle, on the top of the first rectangle, and on the bottom of the third rectangle. So see if you can come up with a figure that will make use of those. All right, good luck. All right, and if we actually go ahead and fold this figure, we end up having this prism, if you will. This polyhedron will look like this. It's a prism, if you will. Also, it has 3 rectangular faces, and 2 triangular faces. So it ends up looking something like this. All right. So that's pretty much what this net will look like. So let's actually take a look at our next part, which is drawing a net. Draw a net from the graham cracker box. Label the net with its dimensions. All right, again, I am not much of a sketch artist, so I'll actually make sure that I can put the image up here, but right for now we can see that it is a box, and it actually has 3, it has, well, actually has 6 faces, a top, a bottom, and it has 4 other sides. The top is a square, the bottom is also a square, or it looks like a square, but let's see what it would actually look like if we were to take this 3-dimensional figure and now we were to break down the box. It will have some flaps, right? But we'll see what those look like in just a second. Okay, so if we were to open this box up into its flaps, well, apparently, based on the dimensions that we have, the bottom indeed is not a square. It just appeared to be a square, but we can see that the dimensions tells us that it's 14. The base is 14 centimeters wide and is 7 centimeters deep. Now, the box itself is 20 centimeters tall. So we have here, we go ahead and take a look at here's the face of the graham crackers box right here, which is the first rectangle. We have a front and a back. So we have the front right here, the back over here. We know that the height on all these, or all this region over here, is going to be 20 centimeters. Based on what we have here, this flap that folds from the face, right, from this face, and it folds back, it goes down 7 centimeters here. So this is also 7 centimeters over here. Let me actually write a better 7. So 7 centimeters over here. And the other flap on top right here, we know that it goes 7 centimeters. This flap that goes on the side corresponds to this side right there. Let me make a better arrow than this. Much better. That side is also 7 centimeters because, well, that's how deep it is. This side over here also is 7 centimeters. So we have 7 centimeters here. And this is 7 centimeters as well. All right. So then that's this length over here. If this guy is 14 centimeters, this is 14 centimeters. And because the graham cracker box does have the front face right here where the branding is at, and that face has another one that's just like it in size, which is this one right here. And if this one is the same size, so we know that it's also 20 centimeters tall, but we know that it is 14 centimeters wide as well, just like its counterpart. So that's why we actually do this. As a matter of fact, we're going to see the application of this when we do the area and volume of three-dimensional figures. It's actually easier if you can realize that you can find the area, the surface area of a three-dimensional figure using this concept of nets. So that's useful to you. All right. Part B. Part B, well, is a continuation of the first one. As you can see, it says draw a different net for this box. Show the dimensions in your diagram. All right. So for this one, I'm going to attempt to draw it. Okay, it's not going to be pretty, but we can actually draw it. As long as it makes sense, we can actually draw it and make it look like it will work. So let's take a look. So we know that it has a face over here like so. Right? It does. I could actually have the same flap over here, and your drawing can be different. It does not matter as long as it actually makes sense. I'm not making it much different. I'm just making a point that you can actually make it different as long as it makes sense. All right. So I'm going to go ahead and make my flap over here look like this, and my other flap look over here like this and like that. All right. So this is going to be 7, 7, 7 over here. This is still 14, and these are centimeters, by the way. I'm just not writing my centimeter units right here. Centimeters, centimeters, centimeters. This is my 20 centimeter. And the top flap and the bottom flap are identical, so this is going to be 7 centimeters, 7 centimeters, 7 centimeters, and so on. This is 14 over here. This is 20 over here. But you get the idea. It doesn't have to be pretty, but when you fold this, it actually will come up to look like that box over there. Is not going to be the most efficient one, which is this one on the first problem is the most efficient one, but both will yield the box. Both will actually yield the box. So that's pretty much drawing a net. So that's my crude image of one, and we can actually laugh at that later. All right. All right, Euler's formula, which we have right here. Now you can call it Euler or Euler, it doesn't matter to me. I call it Euler because that's the way I was taught. The Euler's formula states that the numbers of faces F, vertices V, and edges E of a polyhedron are related by the formula F plus V equals E plus 2. So faces plus vertices equals edges plus 2. That's pretty much what that says. So we're going to actually take a look at how we can apply this formula, and we're going to do this right here. All right. So it says, count faces and edges, then use Euler's formula to find the number of vertices in the polyhedron on the right. All right. So let's take a look at this. We need to find, we need to find the number of vertices in the polyhedron. So we know based on Euler's formula that we have faces plus vertices equals edges. Let me write a better E than that. Edges plus 2. Plus 2. All right. So we have that right there. Now we need to count the number of faces. So let's take a look at the figure. We have 2 hexagons, right? So let's write that. We have 2 hexagons. 2 hexagons. 2 hexagons. And we have 6 rectangles, right? Because if the top has 6 sides, then the faces on the sides has to match the number of sides, right? So this are 6, and the overall shape of the sides are rectangles. So we have 6 of those. So it's 6 rectangles. All right. So we have that, which means that we take those 2 and add them together. And 2 hexagons and 6 rectangles gives me a total of 8 faces. All right. Now we need to find the number of edges, right? So we can do this. So because we're trying to find the number of vertices, so we need to find our edges. So to find our edges, here's what we do. We know that we have, again, 2 hexagons, 2 hexagons, 2 hexagons, 6 rectangles, 6 rectangles. So 2 hexagons, that tells me that is 2 hexagons times the number of sides that a hexagon has, which is 6, which gives me 12 edges. Edges, let me make a better S. Edges. We have 6 rectangles, so that is 6 times 4 sides, right? So that gives me 24 edges, okay, which gives me a total of 36 edges. Okay, but we have to do something here. Okay, it's 36 edges, but this method of calculating the edges has a little difficulty, or a little additional step. When I count this, I'm counting the edges twice. I'm counting the edge of the rectangles, the rectangle meeting the hexagon, and the hexagon meeting the same edge. So doing this makes it that I'm counting each edge twice, because this calculation shows that the edges are counted twice. I need to divide this number by 2 so I can count each edge precisely one time. So because this method again, this method of counting the edges does not take in consideration double counting, I need to undo the double counting by dividing by 2. So we have total edges is what we got, the 36 divided by 2, so we can get rid of the double counting, and that gives me is 18. And this is the number of edges that we need. Okay, so now we know the number of edges, which is RE, and we can go ahead and plug in the numbers into our formula for the number of vertices. Well, the Euler's formula says faces plus vertices equals edges plus 2. Since we're calculating for vertices, well, let's just plug the numbers in. So we have for faces, we know that we have 8 faces, so we're gonna plug in an 8 right there, plus the vertices, but the vertices is what we're solving for, equals the number of edges, and the number of edges is this 18 over here, so this 18 goes over here, plus 2. Then we have 8 plus V equals 20. We subtract 8 from both sides, and we get that V equals 12. Let me make a better B than this. V equals 12. So we have 12 vertices. Okay, so that's one way to do this, actually, using Euler's formula. The other way would be to physically take the figure or look at it and label it. In a figure like this, labeling it might be some cases easier, probably. But if you had a polyhedron that had, say, 12 faces, or it had more faces than that, then it becomes tedious to do it by eye or do it by hand. So Euler's formula becomes better or more effective to find those. All right, now let's take a look at this example for you to do. This one has no drawing, but you'll see how we actually do this. All right, it says use Euler's formula to find the number of edges on a polyhedron with 8 triangular faces. With 8 triangular faces. All right. One hint before I tell you to pause is you might want to draw the polyhedron. Doesn't have to be pretty, obviously, but draw it, and then it will help you quite a bit. Good luck. So in here we have a polyhedron with 8 triangular faces. 8 triangular faces, as you can see. This, by the way, is known as a bipyramidal polyhedron. A bipyramidal polyhedron because it's 2 pyramids on top of, on one on the bottom of the other, and mirrored, if you will. So that's the figure that we need. It has 8 faces. We have 1 face here, 1 face here, 1 face here, 1 in the back. Right there, we have 1 here on the side, so we have 4 faces. The same thing applies here. We have 1 here, 1 on the side, 1 over here, and 1 on the back. So we have 8 faces. Now, so we know that the number of faces, or F, that was given to us to be 8. right? We're trying to find the number of edges. So edges is what we need. Edges is what we need. So do we know the number of vertices? Well, the number of vertices is anywhere that the corners, if you will, the corners of our figure. So we have 1, 2 here, 3, 4, 5, and 6, right? So we have 6 vertices. 6 vertices. So we have, then all we have to do is use Euler's formula, which is faces plus vertices equals edges plus 2. Then we go ahead and plug those numbers in. Faces, we said that is 8, so we plug in an 8 over there. Number of vertices, we found it to be 6, so we put our 6 over here. Then we're solving for the number of edges, so we have E over here plus 2. So 8 plus 6 rather happens to be 14. 14 equals E plus 2. Then we subtract 2 from both sides, and we get that E equals 12. So our answer is 12 edges. All right. So that's what we do here for nets. All right. It's a very short lesson on nets. We're going to be using this a little bit in this unit when we actually do surface area on 3-dimensional figures. So this is the end of this lesson, short and sweet. If you guys have any questions, feel free to send me an email or contact me through Teams. As usual, please do not hesitate to do so. And I'll be seeing you on the next one. Have a good one.